Section 1.1 is mathematics and problem solving. So what we're going to do in this section is we're going to talk about basic problem solving strategy and then look at some different sort of classical cases of types of problems that can be worked in different ways. Okay? So our four-step problem solving strategy is from a mathematician named Polya. The first step is to understand the problem. And these are the kinds of things you might ask yourself when you're trying to understand the problem. Can the problem be stated differently? What is it that needs to be found? What are the things that are unknown? What information is obtained from the problem? What information, if any, is missing or not needed? Okay? So understanding what's really going on in the problems you're looking at. The second step is to devise a plan. And this is where most of our work that we're going to do here in a little bit is going to fall. So the following is a non-exhaustive, that means it doesn't include everything, list of strategies for solving problems. So one is to look for a pattern. Another option is to examine related problems. I know that you've seen that kind of before because you've probably looked for, back in the textbook for a similar problem or looked, for the odd number one that looks like the even one you're on so that you can look in the back of the book for the answer, right? Examine a simpler or a special case. Sometimes if you can break it down into something smaller, you can figure out what's going on and then you can extend it to a bigger example. Making tables or lists is sometimes helpful depending on the data and the problem you're working in. Identify a sub-goal. Sometimes if we can get to one place, we can move on from there. So the idea of getting to that smaller location, that stop in between, is a little bit more manageable. Diagrams. Even if you're not a good artist, sometimes it helps to see a picture of what the problem's asking you to do. Guess and check isn't a totally appropriate strategy as long as it's used in an effective way. Just random guessing is not very effective, but using a guess and check strategy where you revise and re-guess using that information can be very effective. Working backwards, I know you've done that one before too, when you've looked at the back of the book and been like, well, how did they get that answer? Right? And then you're trying to work backwards to figure out where from their answer you can meet up with where the question is. So working backwards. And the last one is one where we're not gonna spend any time in this class. But once you get to middle school math, at some point along the way, making equations can be helpful. So I'm not saying you can't use equations, but that's not where we're going to sort of focus our attention. Okay? Our goal is not to make this algebra class. So if you solve a problem with algebra, that's okay, but that's just not how I'm going to show you how to solve them. Okay? We're looking for things that are a little bit more accessible to a younger child. After we've figured out what we want to try to do, we're going to actually do it. Carry out the plan. Implement the strategy from step 2 and perform any needed actions or computations. Attend to precision in language in the mathematics used. Check each step of the plan along the way, either formally, so that means like actually maybe plugging a number back in and seeing if it works, or intuitively, that means asking yourself, does this make sense? Okay? And then keep an accurate record of all your work. Nothing drives me nuts more when I'm working with my teenagers on their math than to see work scribbled on something and I don't know what they did. Because if I don't know what they did, I can't help them try and figure out what they did wrong. So it's going to be helpful to you as a student and as a teacher to actually be able to see the work that you've done so that you can go back if you do make a mistake and try and figure out what it is you did wrong. Okay? So keeping an accurate record of your work. And then finally, once you've gotten some kind of an answer, checking to see if it makes sense. And there's two ways to check and make sense. It's to check and make sure that it's accurate. Okay, I'm skipped the first one. Reasonable. Does it make sense? I always have this distinct memory of a test we used to give when I was in the University of Kansas, and I did some grading. It's a group grading kind of thing. And the ones that always just made us shake our hands are the students who answered there was 242.37 termites. No, there is not 0.37 of a termite. There's not, right? It doesn't make sense. It just doesn't make sense. And so checking to see if something makes sense. If you actually get a negative answer and it's something that can't be negative, that doesn't make sense. You've got an error somewhere and you go back and you look, okay? So there's reasonableness involved. And then making sure that it's really accurate. Does it answer the question in an accurate way based on the, the information that was originally given? Like truly that is the correct answer, not just reasonable. All right, so we're going to do at least one example today. This is a mathematician by the name of Gauss. And when he was in early grade school, His teacher gave them an assignment, intending it to take them a good deal of time. I'm sure you guys never had a teacher like that, right? It's called busy work. Yes, she wanted them to add up the numbers from 1 to 100. 1 plus 2, that gives you this, and then plus 3, and that gives you this, plus 4, and that should take some time, right? Gauss answered almost immediately. I'm sure the teacher was super excited. So what we're going to look at is how he figured out the problem, and he was obviously brilliant because he's a mathematician, but he did it using patterns. So I want to show you a pattern when you're actually adding up a whole bunch of numbers together that already have a pattern to them. So obviously the numbers 1, 2, 3, 4, 5, 6, that's a pattern itself, right? So the numbers themselves are in a pattern, and then he found a way to find a pattern of summing them up. So let's take a look at this together. All right, so what we're actually going to do is I'm going to write down the letter S as our sum. What we're trying to do is to add 1 plus 2 plus 3 plus, I'm going to put the 3 dots, and then I'm going to put the last 3 numbers. So 98, 99, and 100. Now, we're going to work out written form what he did. Whether his work will look exactly what our work is looking like is not the point. It's the thinking behind it that we're focusing on, okay? So the best way, and this isn't how I used to teach it, but the best way that I saw somebody do one time that was really cool is they wrote this down again, but they wrote it down backwards. Okay, so underneath it we're going to write S equals, and we're going to write 100 plus 99 plus 98 plus dot dot dot, and then 3, 2, and 1. Okay, everybody agrees that those two statements are the same, right? When you switch the orders and numbers around, that's actually called the commutative property of addition, which we'll talk about more later, but you can do that with addition and you get the same answer. Well, here's what Gauss noticed when he did this, okay, is that if you add these together, you get 2s on the left, like you've got twice as much as you started with. But what happens when you add each pair together? They're all the same, right? Yeah. They're all, in this case, because of these numbers, 101. So we have a bunch of 101s. Now that's twice as much as we started with, agreed? Because we added the numbers to themselves, basically, in reverse order, but we've got twice as much as we started with. That's why there's 2s on the left. All right, but in probably second grade these days, but certainly by third grade, you learn that when you add a number together multiple times, there's another way to do that. You multiply, right? That's what multiplication is, or at least one version of it is. It's adding something together multiple times. So what we really would like to know is, well, how many of them are there here? There's 100. How do you know there's 100, Catherine?
Because we're adding up the numbers 1, 2, 3, all the way to 100.
Right. There are 100 numbers because we started with 1 and we ended with 100. That's 100 numbers. Now, if the numbers did not start at 1 and end at 100, it becomes a little bit more difficult to see how those numbers or how many of those numbers there are, and I'll show you how to do that on our next problem. But for the sake of this one, there's 100 numbers. So how do we get the sum of adding 101 together 100 times? It's multiplication. So this is 101 times 100. There are 100 terms added together. Added together, and the numbers that's added together are 101. All of them are 101. So the number 101 is added together 100 times. That's 100 times 101. All right, so what is 100 times 101? 10,100, yeah. So 1 0 and then 1 0 0. And then what would I do? Divide by 2. Now, where did that dividing by 2 come from again? Because we doubled it. So the reason that there's a 2s, the reason that we're dividing by 2 is because we added it to itself. So we have double the number of values we originally had. So this value is 5,050. If you add the numbers from 1 to 100 together, you get 5,050. Okay, so we do have another example where the numbers aren't quite so friendly. That is, they're a little bit less straightforward. This one right here does not start at 1, right? It actually starts at 36. It doesn't end at 100, it ends at 147. But this is a similar problem, right? So we're going to use the same strategy, but we're going to manipulate it slightly when we need to. But there's no reason to reinvent the wheel. Don't do that to yourself. Look and see if you can use something you already know. So we're going to start out with doing exactly like we did in the last one. We're going to write down S equals. And I'm going to write down the first 3 numbers and the last 3 numbers. There's nothing particularly special about 3. I just think that seeing the 3 numbers helps to see the pattern truly works. But if you chose to do it with 2 numbers, you wouldn't be hurting my feelings any or anything, okay? And then what did I do next? Flipped them. I reversed the order, right? So write them all down again, but now we'll start with 147, 146, and 145, 38, 37, and 36. What did we do next? Yeah, we added them together. So we noticed, and the reason we're doing that is because when we do that, all of the sums are the same. Whatever they are, they're the same. So what are they? It's 2s on the left. Let me start there. But what are they when I add the numbers together in pairs like that? 183. So I have a whole bunch of 183s. Now, a whole bunch is not very precise. We really need to know how many, right? So how are we going to figure out how many of them there are? 147 minus what? Very, very close. Minus 35, yeah. So here's how I think about it, because it's easy to get tripped up and just think first number minus, or last number minus first number. If you subtract the first number, that is the 36, you're removing the 36 from the list of numbers. I don't want to remove the 36 from the list of numbers. I want to remove the ones that aren't there. In particular, the numbers that are missing are 1 through 35. Those are the numbers that aren't in this list of 147 numbers, right? There would be 147 if there were, but there are these numbers that are missing. And how many numbers are there from 1 to 35? Well, there's 35 numbers. So the number of terms here is 147 minus 35. So what is 147 minus 35? 112. So there are 112 terms. Okay, so now what? Still have double the value, so still 2s on the left. What do I do with all these 183s, and I've got this 112 now? I multiply them, because that's what repeated addition is it's multiplication. Whoops. So I have 183 times 112, which is what?
20,496.
And then what would I do to actually find the sum? Divide it by 2. And what would that give me?
10,248.
Okay, now let me just talk in general, though. Both of these lists of numbers included all the numbers between the first number and the last one, right? I mean, there weren't any skipped or anything like that. What would happen, let's just go back to this example because it's a little bit cleaner to talk about this way. What would happen if I had these numbers from 1 to 100 like this, but I had only the evens? You'd only have half the numbers, right? It would change. You could write it out, like if it were only the evens, you'd have 2, 4, 6. I mean, you can write it out the same way, right? And we'd have, wait, I said, so 96, 98, and 100. And you can still write out, reversed and so forth, but what actually changes is how many terms you have. You won't have 100 terms, right? You'll have 50, okay? So be careful, not that you're doing the homework tonight on this, but when we do get to the homework and group work, there are some where they skip a number. What if I had multiples of 5? So I had 5, 10, 15, 20, what? You'd have 25, well, not 25. It'd be 20, yeah. How do we get 20? The divided by 5. So why did we divide by 5? It's only the multiples of 5. So however many you're not however many you're skipping, but whatever the multiple list is that you're using, that's actually what you would divide by to figure out your number of terms. So when you're skipping numbers, you have to be a little bit more careful with the how many terms do I have question than you do when you're just listing all of the numbers between whatever and whatever. And we'll have more practice with that later, but we're going to stop right there for today and we'll pick up on Friday.